Morning. This is Grand Rapids Community College's calculus class. We have been talking about applications of definite integrals, including arc length, area of the surface of revolution, and most recently, we did some fluid force and center of mass problems. So, from that homework, does anyone have any questions? 8.3. He said something. What did he say? Can you say that a little louder, please? I still can't hear you. 19. Thank you. Okay, so here in number 19, we have a vertically located, vertically positioned, irregularly shaped plate submerged in water. And the table shows measurements of its width, assuming, actually, assuming they are at identical depths. So they're taking horizontal slices here, so that all the way across that width, the pressure would be the same. And so we're supposed to use Simpsons Rule to estimate the force of the water against the plate. And again, Simpsons Rule is the one where we approximate the integral with delta x over 3. So we have two things here. We have to look at the integral involving pressure, fluid, to find the fluid force, and we have to look at the Simpsons Rule idea. So again, our integral that we're looking at here is ones like this, where the total force is going to be the integral of the mass times the acceleration due to gravity times the depth times the area at that thing, that depth. So let's get back to the application here. I need to know whether we're using meters or, so we're using meters here. So that means we're using metric system, which means we're going to use the density of water as 1,000 kilograms per cubic meter, and the acceleration due to gravity is 9.8 meters per second squared. The depth is going to be given here, and then so this is sort of like the x that they use, and then the width is given down below. Okay. So with Simpsons Rule, I'm going to use a summation to remind you. It's the one that has the coefficients like 4, and then 2, 1, then 4, then 2, then 4, then 2, then 1. I want to find if I can find it for you. There we go. So the Simpsons Rule has an integral from a to b of f of x. It's going to be the delta x, how wide our little intervals are, divided by 3, and then 1, 4, 2, 4, 2, 4, 1. In order to use Simpsons Rule, we have to have an even number of intervals. Okay. And delta x again is b minus a over n. So let's take a look at this. We have measured at 1, 2, 3, 4, 5, 6, 7, which means you have 6 intervals, so this is going to work okay. All right, so essentially, we are trying to find, back out a little, the beginning depth was 2 meters, the final depth was 5 meters. We're using water, so it's again 1,000 kilograms per cubic meter times 9.8 meters per second squared for acceleration. And then the depth is, well, we can call whatever letter we want, x, and then the width, I'll call it w of x dx. This together represents the area at a certain depth. Okay, so with Simpsons Rule, delta x here is going to be 5 minus 2 over 6. 6 because n equals 6. If you check, there's 7 points there again. We counted those, which means we have 6 intervals. So delta x is 1/2. And Simpsons Rule says the integral from a to b of f of x dx is going to be approximately delta x over 3. Now, at the left end point, we just use f of x, and then 4 times f of x1. I gotta zoom out. And then I can just about put them all in here, can't I? 2 times f of x2 plus 4 times f of x3 plus 2 times f of x4 plus 4 times f of x5, and now I'm at the other endpoint, so just f of x6. Again, it goes 1, 4, 2, 4, 2, 4, 1. Those are the coefficients we're going to use given f of x. All right, so pulling out my 9.8 times 1,000 gives me 9,800 out front. Delta x over 3 is going to be 1/2 divided by 3 is going to be 1/6. And then these functions are going to be taken, function values are going to be taken out of my second row of that table. So I have 0 plus 4 times 0.8 plus 2 times 1.7 plus 4 times 2.4 plus 2 times 2.9 plus 4 times 3.3, and then finally just plus 3.6. And again, those numbers in parentheses are out of our table. 0.8 or 8 tenths, 1 and 7 tenths, 2 and 4 tenths, 2 and 9 tenths, 3 and 3 tenths, and 3 and 6 tenths. By the way, I calculated delta x, but you could also see it. If you look in the table, how far does it go from one reading to the next? It's 2 to 2.5, 2.5 to 3, 3 to 3.5. You can see what the delta x is from that as well. Okay, so now we just have to finish calculating this. Two plus 3.4 plus 9.6 plus 5.8, 13.2, 3.6, 6.6, 16.2, 21.2. And 16.8 is 30.8. I should probably get my calculator out to check whether I'm doing that correctly in my head. Okay. Now, since our measurements were only to 2 significant figures at the best, we should say 63,000 here. You don't think that's the right answer they gave? Anyway.
Because I think, like, you have to multiply each of the sections by the depth that they were at.
Oh, thank you. Thank you, Eric. I left out, sorry about that. I wrote it here, but I left it out. Um, Thank you for pointing it out there. So instead of this line I have here, which would be right if I just put the depth in there as well. Let's go back and rewrite this line. And depth started out at 2, and then it's going to go up by a half for each of these spaces, which means I'm going to have trouble fitting it in here on one line, but we'll see here. So all this was okay, except I forgot to put the depth here, and X here would have been at 0.8, it was 2.5. Sorry about that. That should be, these are the things that were added. Put them in here. What do we got? 4 times 2.4 is 3.5. 2 times 2.9 times 4 plus 4 times 3.3 times 4.5 plus 3.6 times 5. So you give us quite a bit bigger number there, actually. So again, I left out the x here in my integral I'm supposed to be doing, which was supposed to represent the depth all the way along. Yep, thank you for, I didn't mean to leave that out. I wrote it up there, but we got to make sure that you include all the parts of the integral. Again, each of these is actually, I kind of reversed them here. This is the width, and that's the depth for each of these. You know, I wrote the other way around up there. Again, one of the things I like about this problem is it's an applied problem where the measurements are taken. It didn't actually try to give you a function necessarily, because a lot of times, as in engineering and stuff, the data you have, but you can't really model it very easily with a function. So here they were just able to take the data itself and come up with a value estimate. Is that okay? know who asked that question out there, but we okay? Okay. All right. How about another one?
41.
Okay. So 41 actually involves a little bit of the center of centroid or center of mass of rectangles is actually pretty easy. It's just right at the center um, of area. So it's just going to be at this, it's easy to find. The center of mass of a triangle is a little trickier. It's where the medians intersect. Um, so how would you find, say, a median? Now, there's a lot of symmetry in this problem. So how would I find, I know on this little triangle on the right, for instance, that it's going to be the median from the top vertex straight down to the base is going to be x equal 1. That's the line it's going to be on. But it's not as clear where the median on the right is going to be, or left, either one, whichever one you want to do. Is there a particular one you'd like to do? I might as well do the one here. The nice thing about the one starting at 0, 0 and going up is the y-intercept is 0. So all I have to do is figure out the slope. And I know that the slope of that median is going to be, now the median again is the point that connects the midpoint on the opposite side, not the altitude. I'm not talking about the altitude or the angle bisector. So, I'll just write my book here. I think I have a pencil in there just a second, just in case someday later I want to erase that. So the top point here is 1, 2, which means the midpoint on this other side is going to be 1 1/2, 1. Which means that if I were to draw the line segment through there, the equation of the line that contains that line segment is going to be 1 divided by 1 1/2, or 2/3, y equals 2/3 x. That's the slope of the line, the median starting at 0, 0 and crossing through there. And we know, again, this median is x equal 1. So the point, the centroid of this triangle is going to be where those two lines intersect. So if x equals 1, y equals 2/3. So the centroid of my triangle is at 2/3. Excuse me, 1 2/3. Okay. And the center over here is also going to be at -1 2/3. That's the centroid of that triangle. Whereas these ones, the rectangles are going to be a -1 -1/2, and -1 positive, excuse me, +1 -1/2. The areas of the triangle, 1/2 base times height is going to be 2. The area of the rectangle is also base times height, which is 2. So all these areas are the same. They're all equal to 2. So we're trying to find a centroid. We're going to add them up. All the areas were 2, so the 2 actually is going to separate out. But if I just look at the x coordinates, for the first triangle, I have 2 times -1. For the second triangle, I have 2 times +1. For the first rectangle, I have 2 times -1. And for the second rectangle, plus 2 times +1. This should all add to 0, divided by total mass is 8, total area is 8. Now, we could have deduced that in terms of the x bar just by looking at the symmetry. The y bar is a little more complicated, just because it's not as clear where it's at. So for the first triangle, again, the area was 2, and we decided that it was at 2/3 was the y coordinate. For the right triangle, it was also at 2/3. For the bottom left rectangle, the y value was at -1/2, and for the top bottom right rectangle, the y value was at -1/2. And then you divide that all by 8. 4/3 and 4/3 and -1 and -1. So I have 2 and 2/3 minus 2 is 2/3 divided by 8 is 1/12. So it's slightly above the origin, which actually is not in the, so my centroid is 0, 1/12. Now that's actually not part of the figure itself. So the centroid is just a teeny tiny bit above the origin. Sort of an interesting, when you have concave shapes like this one where it caves in at the top, so that if you connect the different points here, you go outside the region, it's possible for your centroid to not be actually in the region itself. Okay, Eric? Again, it kind of required, they gave you a hint actually if I would have read through 39. 41 said, look at 39. 39 actually hinted that the medians intersect 2/3 of the way down from the vertex, so that vertical line we could have actually figured out 2/3 without having to do the equations, but it was kind of fun to do some algebra, fun stuff. Okay, so I have a quiz for you guys to do today, based on the last few things. So, and it can be open book if you want. I'll just remind you of the formulas, but if you want to use your book to look at things. For arc length of a curve, that was the formula we used, where if y equals f of x, you had to find the derivative, square it, add 1, take the square root of that, and that would give us, and then integrate that from the left-hand point to the right point, and that would give us the arc length. For a surface of revolution, very similar integral, but we were multiplying that by 2 pi times the radius, and the radius was f of x if we were going around the x-axis. Surface area revolution around the x-axis. I should write that down there. And then we had the same. Find the total mass. We would just integrate the density times the function value. And again, this is one that's from the x-axis up. To find the moment around the y-axis, it would look like that. The density times x times f of x dx. And the moment around the x-axis was the density times f of x squared over 2. And we use these to find x bar, that the centroid or center of mass was the moment around the y-axis divided by the total mass, and y bar was the moment around the x-axis divided by the total mass. So this is a summary of what we have so far. So I'm just going to give you one function from 1 to 2 and ask you to find all 3 of these things. Okay. So, let's get function. Actually, maybe I can squeeze it up in the right-hand corner here, so that you can have these for notes too. Feel free to use your calculator for evaluating the integrals or for finding derivatives if you need to. So y is x to the 4th over 16 plus 1 over 2x squared, the x squared in the denominator. And I'm going from 1 is less than or equal to x is less than or equal to 2. I want you to find the arc length of that curve. I want you to find the surface area if that curve were revolved around the x-axis. And then I want you to find the center, the centroid. And, so assuming rho is constant. So most of what I want to see is the sort of the integrals that you set up, and then the final answer. So again, I don't mind if you use a calculator to evaluate the integrals, since we just did that section. So everybody turned it in out there? Couldn't quite hear, but like I said, about 2 more minutes or so. Blackboard's down temporarily. Let's check back later. It's down. Okay, if you guys could turn yours in, please, if you haven't already. Oh, you can't see what I'm getting, sorry. I'm just doing that. At this point, those fractions are getting, ugly, but we can see what we can do with that. That's 8 times 64, so 3 times 4. Well, the only thing left to do here is divide mass by my divided by this will give you the x coordinate of the centroid, and mx divided by, excuse me, this is mx. My is here, divided by the mass will give you the x coordinate, and then the one I just found divided by the mass of the y coordinate of the centroid. A lot of parabolic stuff. Like I said, the calculator can help you do quite a few of those integrals, but hopefully you didn't have too much issue with that. Did anybody have a question after I went through those? Okay. So again, sort of summing where we're at. This we're going to go 8-4 today, 8-5 on Friday. Then next week's winter break. The week after that, the day we come back, Monday, we'll review. Wednesday will be a test over Chapter 8, and then we'll go on from there. Which means the problems plus, which I forgot to choose, won't be due until the Monday after winter break. So you'll still have after we come back another week, but I will try to put those out on Blackboard and tell you on Friday what those are, for those of you that want to work on them over break, especially like people that are in school anyway. You guys out there can maybe take the time to work on them. But you can also, you don't have to be here next week. So, okay. This next section is talking about applications that aren't science, engineering related. These ones have to do with either economics, a couple of them, or biological sciences, a couple of them. So we just want to talk about a few of those things. Applications of integration that have to do with this. Now, one application from economics has to do with demand curve and demand. Now, demand relates price to quantity sold. Supply, on the other hand, relates price to quantity produced and available, but demand relates price to quantity sold. Depending on whose perspective, this could be quantity as a function of price, quantity sold as a function of price, or it could be price as a function of quantity sold. The way we are going to use it now, and the way economists usually write it, is they write it in the price format. So P of X is the price at which X units can be sold. Or maybe X million units or X thousand units, depending on what the units are that we're talking about. And when you draw a demand curve, it usually looks something like this. Now, the reason it has negative slope is because in order to sell more, you have to lower the price, typically. Occasionally there are those Tom Sawyers among people that can make it seem like it's a better thing to buy if you raise the price, but that doesn't happen very often, really. So typically it lowers. Now, if I end up saying this, say currently, this is the price and quantity, and while your book uses capitals for some fixed value. So this is current quantity, capital X, and price, capital P. If we were to draw a horizontal line over here, this area represents what they call consumer surplus. consumer surplus is that there were a few people willing to pay more than they have to now. Good example would be gasoline right now. Gasoline prices are much lower than they were just a few short months ago, but many of us were still buying quite a bit of gasoline a few months ago. So now we have money in our pockets that we wouldn't have if the price was still $4 a gallon. That means we have surplus compared to what it would have been. What the business people try to do is figure out some way to get you to spend that. But before they do that, they want to figure out how much there is out there. Now, many of you, a familiar one might be going to like Woodland Mall, to the cheap theaters. They still charge similar prices for the popcorn, and you're probably more willing to buy it there than you might at Celebration Cinema, for instance, because if you're paying $8 a ticket, it's costing enough already to get in. Whereas if it's only $3 or $4 a ticket, you might be willing to buy popcorn. And so that extra consumer surplus, they're going to give you something. Now the question is, okay, does it really cost them $8 to make a large pop and popcorn? And it's not even close. So they're charging you quite a bit of money for something that you're willing to buy only because you have a little bit extra money in your pocket that you wouldn't have been expecting to have if you had went to the normal thing. Same kind of thing goes for cars. They'll say they'll reduce the price of the car, and then they'll try to convince you to buy the air conditioning or the whatever, something extra, stereo system, something that they're going to charge you quite a bit more for than it may have cost them in order to recoup that extra money that you had. Okay, but since it involves an area, we can use calculus techniques to figure out what that consumer surplus is. So if I can come up with a function, demand function, what would I get if I just integrated the demand function? Well, I'd get the entire area under the curve. But I only want the area that's under the curve but above this horizontal line. And the equation for that horizontal line is what? Well, y equals that capital P. Okay. And I'm going to integrate from 0 out to capital X. So, based on this little picture, the consumer surplus should be the integral from 0 to capital X of the demand equation minus capital P dx. Now, these two things are constants. The two capital letters are intended to be constants, whereas the demand equation should be some curve that's decreasing. Now, over the short term, a lot of people will estimate a demand equation with a linear function. And in actually economics classes, a lot of teachers will say, you know what, this area looks enough like a right triangle that we're just going to use the right triangle formula, 1/2 base times height, to figure it out. So it'll be P times X times, not exactly. You have to figure out what this intercept is here. And that would represent the price at which you can't sell any, the smallest price at which you won't be able to sell any. That if you reduce it any more, somebody will buy it. That's what the vertical intercept there represents. So if they can find that, then you can figure out this area. But anyway, so for our sake, though, we're going to use calculus techniques. So we're going to do something like this, where we have, suppose my demand equation was given by 500 over x plus 10 minus 3. And capital X equals 40. Say, and again, that might be 40,000. 40, something like that. Oh, I can make that there. I need to figure out so looking at this picture, I have my capital X, I have my demand equation, I need capital P still. To figure out capital P, you have to stick capital X in here, if they don't give it to you. So capital P is demand of capital X, which in this case is demand of 40. Plus 10 is 50, 500 divided by 50 is 10, 10 minus 3 is 7. You know, so it could be $7, or it might be $7,000. Again, the units are dependent on the problem. 40 might be 40,000 units. Apparently our Coke machine isn't working properly for someone right now. So again, now I can plug in here. So the integral is going to be 0 to 40 of 500 over x plus 10 minus 3. That's my p of x. Minus 7, which was my capital P, dx. And I can combine the negative 3 and negative 10, 7 to get negative 10. So I have 500 over x plus 10 minus 10 dx. Which gives me 500 times the natural log of x plus 10 minus 10x, all evaluated from x equals 0 to x equals 40. So I get 500 times the natural log of 50 minus 40 times 10 is 400 minus, and then I got to plug in 0, 500 times the natural log of 10 minus 0. And then I got to figure out what that is. Can't do logs, so I'll just do that. Parentheses. Which is about 404, $405 or whatever. Depends again. All that depends on our units. Okay, so let me back up again. This little rectangle down here that I didn't really highlight yet, but the P times X gives you, price times quantity gives you revenue of the sales of the thing you have. So in our case, 7 times 40 is 280. So from the revenue of my sales, I'm only making 280. And I have more than that in consumer surplus. So whatever product this is, I'm quite interested in trying to figure out how to get some of this consumer surplus, because I could have made quite a bit more money than I'm bringing in currently. And it's situations like that where the consumer surplus is significant compared to your revenue that you're going to go out and try and pursue. Okay, so if I stick with the same one, I want you guys to try one. Well, hang on a second. Do I want? You guys already did quite a bit of work on a quiz. Maybe I'll let us do it this time. I'm going to go back and just briefly look at what if I did the economics thing. if P of 0 here is 500 over 10, which is 50 minus 3, so P of 0 is 47. And this price was only 7, so my scale's off. X was 40. So this height of my rectangle is 40. The width of my triangle is 40. The width is 40. So 40 times 40 divided by 2 is 1600 divided by 2 is 800. So in my case, the actual surplus came out to 405. The economist's idea of using a triangle in my case wasn't very accurate. They overestimated by quite a bit. Double. So sometimes that can cause issues. Now, I need to talk about one other situation that shows up in the book, but I don't know if I'm going to do that one. Just because I have enough other ones to do here. Turns out that there are also something we call the supply curve. And if they give you both demand and supply, now supply is the reverse, it's from the producer's perspective. The higher the price gets, the more they're willing to make and try to sell. And the place where these two cross is called the equilibrium point. And so if someone were to ask you what the consumer surplus is and they didn't tell you anything more, they're assuming the law of economics that says the price naturally flows towards, in a free market, flows towards equilibrium. So in a free market, in theory, this price would drop down until it reached where the number of quantity supplied matches the quantity demanded. Nobody likes to have a shortage, or in a free market, nobody likes to have a shortage. Somebody else can say, well, I can make more money, so you end up making more, and vice versa. You don't want to have too many sitting around. So they naturally kind of, so if the price was over here, it's going to come back down. No matter where you go, it's going to pull towards the equilibrium. In which case, you're going to use that equilibrium point to figure out the consumer surplus. So you might have to find the place where the two curves cross each other in order to calculate the equilibrium. Just so you know, some of the questions are like that. Okay, so another application, biology. And one involving blood flow. You may remember that we had a model for blood flow through a blood vessel. And when I say cylindrical, I mean approximately cylindrical. Of length L, radius capital R, and blood has viscosity eta. Then we had velocity as a function of how far from the center of the blood vessel the blood was as you move your way towards the wall. It's P over 4 eta L times capital R squared minus little r squared. I guess I left out P for pressure. You can analyze this quite a bit. The higher the pressure, the higher the velocity of the blood. That makes sense. the higher the viscosity or the longer the blood vessel, either one of those contributes to slowing the velocity down. And here, the closer you are to the wall, the slower the velocity of the blood cells. Okay, so that makes sense. So the maximum velocity, I think that's what we used as far back in Calc 1, was right at r equals 0. Right in the center of the blood vessel gives you the maximum velocity. What we're interested in is the total blood flow. If you picture a cross-sectional area here, so in a cross-section of a cylinder, looking at it from this way, it's going to be circles, and we picture, so this is supposed to have radius capital R, and now we picture going out a certain radius from that. I didn't draw that very well. But this little radius is lowercase r. And everything, all the blood that is at that radius should have equal velocity because it's the same distance from the center of the vessel. And so that's where this 2 pi r comes from, is that at that radius, 2 pi r, of course, 2 pi r dr gives me the area of that little slice. But I'm making a slice here that's not a rectangle. It's like a ring. Okay, with dr, we haven't really talked about polar coordinates yet, or cylindrical coordinates. You won't learn those until you get to multivariable calc. With polar coordinates, this is similar to polar coordinates here, where the radius r represents how far out from the center I'm going. But the 2 pi r dr represents the area of that little ring, the little washer, and then I'm multiplying by the velocity. So if our model up here is correct, I'm going to take that thing and stick it in here for v of r. So it becomes there's quite a few constants here, the 2 pi, 4, eta, L, and P. We're assuming constant pressure for right now. I'll write that down here. So this is going to be pi over P over 2 eta L. And then lowercase r times uppercase r squared, and lowercase r times lowercase r squared. So I get uppercase r squared r minus lowercase r cubed. So here I get lowercase r squared over 2 minus lowercase r to the 4th over 4. This one has a capital R squared times it. When I plug in 0, I'm just going to get zeros. When I plug in capital R, this first part's going to give me r to the 4th over 2. The second part's going to give me r to the 4th over 4. So I'm going to end up with r to the 4th over 4. So this is going to be pi e over 8 eta L r to the 4th. Is that okay? They're going to have a few questions. Most of them are actually going to be plugging in. Although there's some interesting things to think about with this. If we assume the flux is constant, F, capital F is constant.
Someone has a question.
Yeah. I can't still quite hear you. So this ends up being r to the 4th over 2 minus r to the 4th over 4, which is r to the 4th over 4. And when I take the r to the 4th over 4 from here, times the constant in front, the 2 that's there times the 4 gives me an 8. Okay. So we can assume the flux is constant, that our body wants to have about the same blood flow if possible. And then assume that our radius of our blood vessel is getting smaller. So let's suppose that R1 is maybe 3/4 of R naught. How does the pressure change? This doesn't have to do with calculus. But it's an interesting question to ask. It's more the type they ask with this one. So if F is constant, then when I put in my zeros, my initial values, pi p naught over 8 eta L r naught to the 4th has to equal pi p1 times over 8 eta L r1 to the 4th, if the flow is constant. And your body's going to want to try to have that happen. So now I'm going to solve this for P1. The pi's cancel, 8 eta L, 8 eta L, those will cancel. So P1 equals P naught, R naught to the 4th divided by R1 to the 4th. So based on this up here, again, the radius of my artery has gotten smaller as I've eaten all that great food. And from here, I get that R naught over R1 is 4/3. Oops, I lost you. Just taking that, if R1 is 3/4 R0, then R0 over R1 is 4/3. If I take that to the 4th power, it's 256 over 81. So my new pressure equals my old pressure times 256 over 81. So, although my radius is only 3/4 of what it was, in order to get the same flow, the pressure has to be more than 3 times what it was. Which can cause problems. So you really don't want your radius to shrink very much. Because either it's going to affect the blood flow, in which case you're risking stroke and other heart ailments, or from the fact that the flow's bad, or you're going to have a good flow, but your pressure is going to have to be high, which causes all kinds of other heart problems. So okay.
Is that from like cholesterol buildup?
It could be from cholesterol buildup. Yeah, exactly. That's the idea. Plaque buildup, I think they call it. Yeah. Okay, so another application. Still talking about volume pumped per time. Similar idea. Cardiac output, which is volume pumped per time. So in this case, they want to try to measure the cardiac output. So one way they try to do that is they put dye in their blood, a certain amount of dye in their blood, like small, like 10 milligrams, 5 milligrams, somewhere in there, and then they measure how much dye there is at every so often. So if C of T is the concentration of my dye, then eventually all my dye should actually flow through wherever I'm measuring it. So, and A is the total amount of dye. Should then equal approximately the summation of my concentration times the flow rate times the delta T. So this is a concentration at any one time. I'm going to multiply it by small time intervals and times the flow rate, which again, we're assuming this is constant. If we were to take the limit then, as number of intervals goes to infinity, this is going to approximate the integral from 0 to when I'm done, the dye stops, the dye's all gone. So that's what capital T is going to represent, the time till the dye's gone. I'm going to put the delta T and the C of T together here. So C of T dt times F. And then to find F, I'm going to divide. So some of the homework questions might involve a formula like this. So look for the ones with cardiac output. They'll tell you something like the amount of dye that was initial was 10 milligrams, and then they'll give you a formula for CFT, or they'll give you a table of data for CFT as you go through time. And ask you to use Simpsons Rule like we did last night, something like that. Except this time there's no T involved there, so I won't be as likely to mess up and forget something. But okay, so that's another application. One more here.
I can't see what's above the E.
So here's a possible calculus kind of question. It involves both this semester and last semester. So a surge function is given by something like this. A and B are constants, depending on the type of drug and the person themselves, amount that was dosed. So A times T, e to the minus bt. And a graph of this thing looks something like this. So it surges up to some maximum and then kind of slowly comes down. Now from calculus 1, how would I find out where this maximum was?
Set the derivative to 0.
Yeah, find the derivative of this function, set it equal to 0, you could find a t value, and then you could plug that in to figure it out. And it turns out that for surge functions, that maximum occurs at time 1 over b. I don't know if you guys have had this class before. We also found that the inflection point over here on the right, that it changes from being concave down to concave up. To find that point, I'd use a second derivative and set it equal to 0. Turns out that's at 2 over b. So the maximum value here is c of 1 over b and times up, so I'm going to have to just write the integral down here. So c max is what I get when I plug 1 over b in. How do I find average value? That was one of our applications from a previous chapter. So average value over 0 to some capital T is going to be 1 over T, capital T minus 0 times the integral from 0 to capital T of C of lowercase t dt. And we want to know when that's equal to 1/2 C of 1 over B. capital T? That kind of question. And it may not be a half, you know, you're trying to figure out when should you give them another dose, you know, so that the average amount of some drug in their bloodstream stays within certain boundaries. So, okay, so try some of those for Friday.